Thanks, Andres. And thank you everyone for coming to this seminar. And the topic I'm going to present today is about the predicting of field scale yield. And as just mentioned, I am now a postdoc scholar at QAAFI, and now I'm working with Andres and also Professor Graham Hammer here. And what we are trying to do is to develop an integrated approach to kind of translate what we see from satellite images into like crop years, crop productions, and also some other crop statistics at fine scales. And this is also one of the major tasks outlined in, I think, Andres' QCAS project, which is funded by the Queensland Chinese Academy of Sciences Collaborative Initiative. And it is also through these projects we had close communications with colleagues from Chinese Academy of Sciences, like Dr. Yan Zhao and Professor Bingfang Wu here, and to deliver this work. So through this talk, I want first to give you guys a brief background about yield and yield predictions to really understand the market of developing the proposed approach here. And then I want to talk a bit more about the details about for yield predictions which would help us to understand what are the gaps, what are the challenges, and also what are the opportunities. And then I will focus on how we work with these high performance remote sensing images and also the crop models to develop our approach. And then followed with the model validations, the model applications, and also the implications of these results to the relevant industries. Okay, first about the crop yield. So basically this is really an important metric to determine the efficiency of crop productions. And it is also quite an elementary concept in crop science, which we normally know quite well. And this is also the metric very significantly related to the food security. As we can see in the diagram here, the overall increased what is average crop yield over the past like 15 years, basically a major contributor to meet the increased demands for the ever increased demands for the along with these ever increased populations, and also the information on yield could help the farmers to compare their crop yields to the yield potentials to understand how well they are competing. And the bulk handlers here, including the transportation companies, the storage companies, and also the exporters, we also need this kind of information to decide how much money they will be going to pay for the storages, the transportations, and also groceries. Also, although this is an important metric, it is still a challenge to get these yield predictions that before the harvest actually takes place due to its large variabilities, both spatially and temporally. For example, in Australia, as presented in the plot here, the long-term yield records since 2000 presented an overall increase during these 20 years, but subject to substantial annual variations. An important reason that caused this variation is the ever-changing climate conditions. For example, in 2016, the above average precipitation from early May through to the end of crop season compared to the dry conditions that prevailed over most of the previous years basically lead to this substantial high yield in this year. While in the 2017, the very much below average rainfall mainland southeast lead to the very low yield which yield levels, especially for New South Wales and southern Queensland. So basically the importance of accurate information on yield and the challenge of getting these accurate predictions formed our motivation to continue this traditional research topic. So imagine if we can really map the yield across large regions, regardless of the climate conditions. We can then identify when and where we are actually expecting the risk of low yield, and then we can target at these regions for appropriate management interventions to improve food security. So move on to the approaches for predicting yields. Theoretically, these yield predictions are highly reliant on the quantitative relationships of the plant, environmental, and soil interactions, as we outlined as demonstrated as models here. Depends on the specific methods or algorithms applied in the model here. This model need to be fed with information or data on the identified factors that actually affecting the crop yields, which then these factors are converted to yield as output using the quantitative relationship implemented in the model here. But a traditional way of getting these yield values is kind of independent from this model approach. It is primarily based on field surveys. We know in a lot of regions across the world, they use census statistics to capture the dynamics of crop yield at state or even national scales. Since it is based on field surveys, it can get relative accurate estimations on the farms being surveyed. But it can be really problematic when get regional statistics. And collecting data in the field can be very time and resource consuming. So basically it is impractical for frequent surveys covering large areas. So another constraint of this census approach is it is very obsolete. That means the census data is actually released year or even years later after the data was actually collected. So this is about remote sensing technology approaches, and this technology have been also extensively studied and used for crop yield applications over like the past 4 decades. Basically, the remote sensing is the art of detecting objectives and without the physical contact with objective. In this case, the objective is the crop canopy, of course. And an important characteristic of remote sensing is as human eyes can only see the visible section of the spectrum, remote sensing can see the full spectrums and over large areas. That means much more detailed information about the canopy that potentially related to the crop yield. And what's more important is remote sensing is able to constantly capture images for the same field at a scheduled frequency, which allow us to check physiological progresses of these crops, and therefore provide us with this sequentially updated information about the crop status during the entire crop growth period, which with only minimal neighbor inputs. And a straight way of using this reflectance information captured by remote sensing is through developing different forms of vegetation indices, which basically the combination of different spectral bands to reflect different aspects of the canopy's characteristics. For example, in here we have the enhanced vegetation index and like the normalized differential vegetation index here, which both these indices using the reflectance information within the red and the near infrared bands to reflect the canopy structural status. And we also have the chlorophyll vegetation index, which use the reflectance information in the red edge bands, which use this information to reflect the level of chlorophyll contents within the canopy. So here are some examples in the literature to looking at the relationship between these vegetation indices and the crop yields. And we can see most of these studies actually find fairly good linear relationships between these two, which means we can very easily to translate this vegetation index into crop yield. But the problem with this method is most of these relationships are empiric. And if we really look into the literature, people have tried to do this for 40 years. And out there probably already hundreds of publications on this. But if we look into each publication and everyone publishes a different equation, and this is something really challenging. Because if I am going to extend this to a large volume of fields, which equation I'm going to use? So this is the problem. And I will get back to this point later to show you guys how we are trying to do to overcome this limitation when adopting remote sensing for yield predictions. Well, the next approach for yield prediction is using crop models. And crop model simulation for yield predictions basically received moderate success since it is normally adapted with local crop varieties and environmental conditions. But the challenge associated with this method is this we normally call model parameterization procedure here is normally very tedious, very time-consuming, and also have too many low unknowns. Some model like this normally requires a lot of input data, accurate input data on soil and water conditions, the crop varieties, the management practices like irrigation, fertilization, and also need information on weather conditions. So any uncertainties that are associated with this input data will be propagated to the final output of the yield predictions. So this also limited this approach to be applied at field scale across large regions. So out there in the literature, there are already being developed these types of approaches for yield predictions. Well, the reason we are doing this research is not to say, no, this research or this approach is not good at all. The truth is, these approaches are developed with pros and cons. And what we are trying to do is to use some of the pros of each approach to develop our method to meet the objectives we identified here. The two objectives here is, the first, we want to do it in an operational manner. And the second is we want to do it at field scale. So to do it operationally, we will need to develop a robust algorithm that would work both from local to regional scales. And to do it at field scale, we determined to deliver practical guidance information for a diversified group of end users. So to achieve these two objectives, we will need accurate data on biostatistics surveys to train and validate our models. And we will also need phenological information from remote sensing at large scale, for large scales at fine scales with fine resolutions. And we will definitely need the crop responses simulated with crop models to reflect the different responses to the different climate and environmental conditions. And here is another two important reasons or preconditions that will support us to do this research. The first reason is Andres and the group have already developed the platform for major crop yield predictions based on the simulated crop stress index across the major crop production regions in Australia. And this model we call Ausweight could actually accurately predetermine crop stress, and which would explain more than 90% of the yield variations at shell scale. What we want to do is to incorporate this crop stress index in our remote sensing models to field scales. And another reason is about the resources nowadays we can access to. For the past 4 decades, remote sensing technology have been developed quite fast, which provide us multiple choices of image sources. But there were always a trade-off between the spatial resolution and the temporal resolutions. For example, this early stage sensors can provide us daily images, but at a coarse resolution, like less than 500 meters. Well, these Landsat images, which was launched in the mid-1970s, has the resolution of 30 meters, but its temporal resolution of less than 16 days is actually still insufficient for capturing the canopy or the crop phenological dynamics at field scale. But now we have this Sentinel-2 data from ESA, or the European Space Agency, with this 10 meters resolution in every 5 days, which really gives us the opportunity to look into each field and the phenological dynamics for these fields. And more important is this Sentinel-2 data actually process more spectral bands, especially within the range of near-infrared and the red edge bands, spectral sections, which means more detailed biophysical information that can be used for these crop monitoring studies. And the last but also very important is nowadays we can access to the cloud computation platforms such as the Google Earth Engine here. These kind of platforms allow us to handle these high spatial resolution, high temporal resolution satellite data more efficiently on the cloud side instead of reprocessing it locally with our like 2-core desktop computers. And also there is a large group of scholars that stay quite active in the spatial science communities like the Stack Overflow or GitHub, where we can really easy to get supports and to learn how to manipulate these high-tech computation powers. And in this study, we also used this Google Earth Engine to manipulate our Sentinel-2 data across basically the entire Australia and to test and apply our approaches across these large areas. So today we have been applied our approach to 3 different regions across Australia. We developed our approach in the Mauritius in here. We got detailed field yield data, and then we applied the approach to another group of fields across the northeastern Australia, where we also managed to get detailed harvest data. And then we applied the approaches to the entire wheat belt region across Australia, where we managed to get some validation for as well. And here is to show you how the remote sensing data looks like in the area here in a more visually way. So these are the fields we are working on in Mauritius. And as you can see, the advantage of these Sentinel-2 images in terms of spatial resolution, especially when you compare the overlaid modest pixels here, and one can hardly tell where the fields are. And for the Landsat images, it seems okay in terms of spatial resolution, but when we turn to the number of clean images, which means the images that's free of cloud distributions over these field regions, the Google Earth Engine actually returns much less images for Landsat rather than the other 2 datasets. So it then becomes an easy decision to have Sentinel-2 as our target remote sensing data source. And after the selection of data source, another important step of a process before we apply the images is we need to do this atmospheric correction. So the spectral information in the image acquired by the Census on board the Sentinel-2 satellite at the top of atmosphere is influenced by the factors, including the atmospheric absorption, the scattering, and also the sun, the target, and the census geometry. So therefore, because of this, the reflectance data captured by the sensors at the top of atmosphere, and it's not totally coincide with the reflectance data we acquired at the canopy surfaces. So to emulate these atmospheric effects is actually quite critical for developing a robust algorithm which aims to be applied to large regions where the atmospheric conditions will very likely to change intensively. So to decrease these atmosphere impacts convert this top of atmosphere reflectance into surface reflectance, we used a radiative transfer model called 6S, or the second simulation of the satellite signal in the solar spectrum model, to do this work. And again, the model is implemented in the Google Earth Engine API, which allow us again to use the cloud resources to conduct the correction. And the original Sentinel-2 images provided us the metadata to determine the sound, the objective, and the census geometry, while the instant atmospheric conditions, including water vapor, the ozone conditions, and also the aerosol optic thickness, are determined using the global products which were daily updated with other satellite sensors. And here is a visual comparison of the top of atmosphere reflectance with the surface reflectance, which also tell us the importance of to do this kind of correction. And here is another comparison of the spectral index calculated with the corrected and uncorrected images, which can show us the bias when we're using the uncorrected index to calculate these vegetation indices. And this also reminds us of using the uncorrected images for the quantitative analysis in the following calculations. So with the previously corrected images, we then derived this set of vegetation indices to determine their efficiency in accounting the wheat yield variabilities between the fields. And as I previously mentioned, vegetation index basically is the transformation of multiple spectral bands which allowed us to interpret the variations in canopy structures or the photosynthetical activities. So in here, we then grouped these select indices into the canopy structure related and the chlorophyll related vegetation indices, into these two groups. The first group mainly used the reflectance information in the red and near infrared spectral bands, and the chlorophyll related indices mainly used the reflectance information in the red edge bands, which are widely accepted that these reflectance information are highly related to the chlorophyll contents within the leaves and the crop canopies. And then we started testing the models using these Sentinel-2 derived vegetation indices over the training fields in Maurice Shale. And the field level yield data we collect covered 89 fields and covering 2 separate crop seasons. And the reason that we used used both seasons of the yield data is because these two seasons is actually experienced totally different climate conditions. For the 2016, a major portion of the precipitation was occurred during the winter crop growth period, But for the 2017 season, a major portion of the precipitation was happened during the fallow period, and significantly lower, below average precipitations were observed during the crop growth periods. And what this lead to is substantial higher crop stress status for the 2017 season, and also lead to the substantial differences in the yield levels for these two seasons. We liked this wide distribution of yield data, which provided us an ideal training data set to develop a predictive yield model, which has the potential to be applied to large regions which are characterized with diversified climate conditions. And here I show you the scatter plots to demonstrate the contribution of this vegetation index on the specific days during the crop growth period that to the ultimate crop years. And basically the information from remote sensing at the early stages, let's say before June, and at the late stages, for example, after the early October, when the crop canopy starts to turning brown. Basically, information from these two periods actually provide us little indications about yield levels. But during these two periods, vegetation index actually explain roughly 50% of the yield variations. So in this way, we can see the potential of using this information for yield predictions. And out there in the literature, there are similar analyses and methods to develop yield prediction models. But obviously, we don't want to do it in this way. And the reason is quite obvious when we check the vegetation index profiles here. Suppose we are going to use the image showing the highest correlation with crop yields here, which is August of 11. Then we probably got relative good predictions for these fields. But for the rest of, for this part of the fields, showing totally different phenology shapes, and the 11th of August is still a relative early stage of these crops. The predictions for these fields can be significantly wrong. So to overcome this situation, we decided to turn these remote sensing observed vegetation indices into some biophysical metrics to characterize these phenological progresses. To do this work, we first use these vegetation index profiles to identify the crop growth periods for each field. And then we use these using the vegetation index profiles during this period to derive the biophysical metrics. In this case, here the rate of growing up, the rate of senescence, and also the maximum value of vegetation indices. By doing this, we no longer need to worry about the location of the fields and when the crop is planted, but only focus on the relationship of these metrics with the crop yield levels. And what we do then is we run the regressions of using these each metrics against the yield data we collected. And as we can see from the results here, these metrics with biophysical meanings actually explain more than 70% of the yield variations. In most cases, this is much better than using the single date vegetation index values. And then we start thinking what if we combine the variables with structuring information and the variables with chlorophyll information together. Because in this way, we will have more information that entered into this model, and in this way, we can have better yield outputs. So to proceed, we tested the combination of one structural related index plus one chlorophyll related index, and here is what we got. So basically, using two kinds of indices actually marginally increased the level of variance explained by remote sensing, but the prediction error actually decreased by like 20% from over 1 ton per hectare to 0.8 ton per hectare here. This is a good improvement we are expected to see. And then we incorporated the crop stress index simulated with the Aussie wheat in the analysis. So basically, the stress index adopted in this model is reflecting the level of water limitation during the crop growth periods, and is generally represented with the ratio of actual evapotranspiration rate and the potential evapotranspiration rate. And this is a published work by Andres. And if you guys are interested with the biophysical background of this index or how this index was simulated, you can turn to the paper here for more details. And here is the model statistics. So basically, this integrated model could accurately predict field yield with an R square larger than 0.9 and with the root mean square errors at about half ton per hectare, which further decreased by like 35% when compared to the models without a stress index. And when we validate the models, it is also works very good as well. And in here, we are validating the predicted yield on the y-axis against the observed yield on the x-axis. And we can see from the results here, most of the predictions stay very closely to the one-to-one line, and which means the models is actually doing pretty well. And when we turn to the statistic of MAP, which is the mean average percentage error, most of the fields are showing errors well below 20%, I think. And especially for the fields have these high yield levels. But for the fields with extremely low yield levels, they are presenting relatively large prediction errors. A possible reason we think this is due to the different field extent that captured by the producers and the remote sensing methods. For the producers, this low yield levels probably means the field, parts of the fields actually subject to crop values, and the values here is actually aggregated from the remaining parts of the fields, where the crops are not totally failed. But for remote sensing, the values or the yield values is estimated for all the regions, all pixels that is detected with green canopies during the entire crop growth period. So this also leaves us the space to think about masking out these actually crop valued regions before applying the models. And here here is about another really exciting thing about this really high resolution satellite images. That is, we can not only get this sort of field averaged yield predictions, but also the potential of detailed yield variations within each field. And this map here is a preliminary result when we apply the models to 8 pixels within within the fields. And in this way, by identifying the low yield, high yield regions within each field, we are very likely to assist the producers with better informed decisions like targeted irrigation schemes or nitrogen rate applications and so on, which would lead to better profitabilities. And then we apply our approaches to another 14 fields across the Northeast Australia, where out of these 14 fields are located still in Murray Shire, which is about 13 kilometers away from the training farms, and the rest of 6 fields are located in South Queensland, which is about more than 300 kilometers away from the training farms. And here is what we got about this. Here is the results we got. And again, we can see the predicted yield on the y-axis and the observed yield on the x-axis actually showing very good correlations with a R-square at 0.93. And one might say the models seems to slightly underestimate the yield as this scatter plot, all the points are actually distributed below this one-to-one line. And as we can see from here, this differences is actually quite small, and which is also evidenced with the overall small MAP or mean average percentage errors for almost all these fields. So this result here is not perfect, and but given that this model is actually applied to these fields covering 2 different seasons across these large areas, and with totally different climate conditions, this actually eased us from worrying about the low yield, high yield regions, and also the climate condition changes through time and space. Then, therefore, provided us a real operational methods to be used for these large-scale yield predictions. And then we took our analysis to a large stage by applying the approach to the wheat belt across Australia. And to test how it works, we collected the National Paddock Survey data, which basically provided us 45 data points. And about this, one thing we need to point out is this survey data is actually point-based, and the yield data for each field is actually averaged for each 10 meters radius and at several locations within each field. So this basically is not really a field level data, and which is a bit different from what's the model we developed for. And in this study, the yield value we used to validate our model is the average yield levels for each field based on the several surveyed points in each field. And here is the vegetation index profiles for all these fields across the wheat belt. And from this, we can see the level of variabilities for all these fields, and one can easily tell the difficulties of predict yield levels for all these fields using a single model. And let's see how our model works in this case. So again, we used the Google Earth Engine platform to simulate the structure and the chlorophyll-related indices from Sentinel-2, which we identified as efficient predictors for crop yields. And then we run the Aussie model to get the crop stress status for both the 2016 and the 2017 seasons. And then we use this matrix to drive our model. And then here is what we got. So basically, our model could explain about 70% of the yield variations across the entire wheat belt, and with the root mean square errors at about 1 ton per hectare. This is typically for the 2016 season, while for the 2017 season, the prediction errors is relatively large. But given that the very limited data points for this season, we are still quite happy and quite confident with the model we developed. And again, this method these results we got so far is not perfect, but it does provide us a operational tool to assess yield levels at fine scale, and therefore the potential to identify the regions that has the risk of abnormal yield levels, then which would need specific interventions towards future food security. So, taking all the previous together, now we have get to the point that this high revisit frequency, high spatial resolution, and the fine spectral resolution basically makes Sentinel-2 an ideal data source for the field scale crop years studies. And also the Sentinel-2 structure and the chlorophyll-related vegetation time series allow us to derive the biophysical metrics that showed significant moderate correlations with field level years. And when we include the simulated crop stress index into the yield models, it actually significantly increased the predictability of our prediction models across large areas. And even though the models we got so far is not perfect, and we are still collecting additional data to calibrate these models, at this stage, we still believe this location-specific yield monitoring and the prediction results will enhance or have the potential to enhance industry and the producers the ability to better handle the volatilities in crop yield fluctuations across the supply chain. And at last, I want to take this chance to thank the department and the UQ and also the QCAS project for all the resources to support this work. And also thanks for the Paradox Survey project which provided us the very large field data to validate our models. And also my special thanks goes to Andres and Professor Graham Hammer for all your ideas and the efficient communications during this work. And finally, thanks for all the involved teammates from our Chinese Academy of Sciences partners for their support in doing this work. And thank you. Thank you for your attention.